All right. Okay. Okay. Compiler construction number 14. So last time, we finished up um, garbage collection, which was the extension of our language R3, where we had vectors and heap allocation. So what we're going to do today is we're going to do another extension of the language. We're going to go from the R3 language to the R4 language. Now what's going to be different about it? Basically what we're going to do is we're going to add function calls. And that's going to be a pretty exciting feature that's going to have a lot of, it's going to cause a lot of things to change. So our types are going to increase. So we're going to have functions which go from one set of types to another type. So this is the domain, and this right here is the range of the new function. We're going to extend our expressions to have applications. And applications always have the function that you're going to call and some number of arguments. And then we're going to add a new category called a definition. And then a definition, we're defining a variable, and there are a certain number of arguments, each where we specify what the type is. And then we also specify what the return type is and the body of the function. And then we are changing our program type to have its info, program, its info, and then we're going to have a sequence of definitions and then an expression. So these are the new stuff. So here's an example program that we could write. We could write define even question mark that takes in x, which is an S64, and returns a bool. And it would say if equal x0, then return true. Otherwise, return odd of 1 minus x. Close the odd, close the if, close the define. And then another define for odd that says x of S64, bool, and then we'll have an if of x equals 0, and we'll say false. And then otherwise, we'll say even question mark of x minus 1. Close that, close that, close that, close that. And then we could have the body. So this is this whole thing is inside a program. Here are the definitions, and then the actual content would be something like a call to even question mark of 99. Okay, so this is an example big program. And like before, we're going to have to go modify every little piece. Now here's a few important things to realize. These variables right here that define the thing, they can be used anywhere, which means that you could have like a vector full of functions. So like this position right here, the application position, is not a var that must be one of the functions. Instead, it's any expression. So you could have like an if statement that says, if this number is less than that number, then call the even function. Otherwise, call the odd function. So this expression right here really is any expression. There's no restriction on what it is. Yeah. Okay. So we're going to start working through all the different things that we need to change. We of course have to modify our interpreter, and I'm not really going to talk about how you do that because it's just like doing a big step interpreter in the OPL class. But we do need to update our type checker. So what we're going to do is we're going to extend our type checker so that it's going to have, so it used to be that we would describe the type checker as saying gamma proves that E has type T. And what we're going to do instead, this new thing, is we're going to say that it says in the context of delta, gamma proves that E has type T. Where this right here are the top level functions, the top level funds, and this right here is the local variables. The idea here is that the top level functions, notice that they can be recursive with themselves and with other ones, and so we need to treat them specially, basically. So essentially all we need to do is we need to say what happens when you we need to say what happens when you type check an application, and we need to say um, how to initialize the gamma environment. So sorry, the delta environment. So for instance, if we're type checking a program, something definition ... E, then this is going to type check, and I'm going to draw the line underneath because I forgot to draw it in the right spot. Basically what we're going to do is we're going to say that this is true if delta proves that this definition is type sound, and if delta of empty proves that E has some type T. Let's just put this over here saying that it has type T. Okay, now what does this mean? How do you type check a definition, and what is gamma? Sorry, what is delta? So delta is going to be equal to the empty mapping, where basically each variable, so we'll say def0, that's like the function defined there, is a function that goes from the domain 0, 0, ... domain 0, n to range 0. And we do that for each one of the things, where def0 comes from whatever the variable defined there is, the domain is whatever it says. So essentially what we're going to do is we're going to assume that the types given in the definition are accurate. But we also need to check them. So how do we check a definition? And I'm going to put a little swaparoo here to say that this is the conclusion and here's the premises. So similarly, so now we'll write the one for how to check. So we'll say that delta proves that define of v x type 0 ... x0 through xn type n rty e, it proves that that is type sound, or is typable, if we can prove that delta gamma proves that E has type return type, where gamma is equal to the empty environment extended with a mapping from x0 to type 0 ... xn to type n. So essentially what we do is we check the body expression with the initial definition environment and an empty environment. And then when we check a definition, we assume that all of the variables are present with their appropriate types, and then we check the body expression. Okay, now what else do we need to do? Well, what we need to do is we need to, let's get rid of this. What we need to do is we need to update the rule for variables, because it used to be that the rule for variables looked like this. It said, it didn't say delta. Well, let's just imagine that it said delta. It would have been something like this. Delta gamma proves that a variable x has type t if gamma of x equals t. Well, we need to add another rule that basically says it has type t if delta of x says t, and gamma of x is bottom, meaning that it's not listed. Okay, so basically this says when we look up a variable, we look in gamma first, and then if it's not in gamma, then we look at delta. Now here's kind of another thing that we could do. Remember how one of the things that our type checker needs to do is it needs to tell us the value of every variable. The other thing that it could do is it could transform this x into a function reference x. The idea here is that we want to tag variables with whether they are function references or not. This is not something that we expect of the user input, it's something that we can do inside of the compiler. All right, the last type checker rule that we need to do is for applications. So we'll say that delta gamma proves that an application of an operator to the operands er0 dot 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 ern has type rty, provided delta gamma proves that erator has the type arrow ty0 dot 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 tyn, and rty is its result, and delta gamma proves that er0 has type ty0 through delta gamma proving that ernd has type tyn. So essentially what we do is we check to make sure the operator is a function and that each one of the arguments has the corresponding type and that the number match, that the number n matches the number of types here. Okay, so then what that can do is that allows us to, type check our programs. So let's look at a simple program that's going to be kind of our test case for doing compilation. Actually, is this one that we want to do for a test case? Let's just, I just want to be really clear about the fact that this erator could be anything. So like, here's an example of a valid function, of a valid program. We could define f as taking an x and returning with this an S64 and returning an S64, and what it does is it adds 1 to x. And then we could define g as what it does is it takes in an x and it multiplies them together. So it does times of xx. And then we could write a function that was like this, where we wrote, let, actually let's not even bother with a let. And then we could write if, let's write if equal read is 0, then return f, otherwise return g, close the if, and then send in another read. Okay, so this is a valid program where the function we're calling depends on what number comes in. You type in a number, if it's 0, you do an f, otherwise you do a g, and then you read the result. Okay, so now how are you going to do random code generation? Well, like with vectors, there are an infinite number of functions that we could generate, each with different types. So essentially what you'll want to do is you'll want to figure out some way of having a small number of example functions. So for instance, kind of the way that I would recommend doing it is what you could do is you could basically, in your random generator, sometimes generate n random functions. Where each one returns a random type, and takes a few arguments. Now, when I say a few arguments, maybe you would have it like take 0 arguments, or like between 1 and 6, or maybe a lot, like 16 or something like that. So just pick a few random arguments. And then essentially what you're going to do is you're going to generate functions that are like, okay, well, we're going to generate f, which goes from int to int, and then you're going to generate g, which will go from bool to an int, and then maybe you'll do h, which will go from an int and a bool to a bool. Okay, now the way that you generate these functions is just by having access to these integers, and you just use your normal algorithm. So essentially, like, these become variables that you can sort of like prime your set of possible things with. And then what you do is you take the fact that these functions exist, and then you record those as potential rules for the rest of your code generator. So maybe in a context where you need to generate an integer, it'll generate a call to f. So that's kind of the idea. Okay, the next thing that we want to do is we want to talk about how to do optimization. Obviously, optimization of functions is really important. I mean, the main optimization that we want to do is we want to do inlining. So the idea of inlining, so optimization, the main thing that you want to do is you want to do inlining. So here's the way to think about it. If you have a call to app where we have an operator with E0 through En, and you know that erater is equal, i.e. after optimization, to some particular definition where we have x0 of type 0, ... xn through type n with some return type and some body. Okay, then what we can do is we can optimize this into a let where we let x0 equal e0, we let xn equal en, and then we do this inside of the body. And then we go off and we optimize that. Okay, now why is this going to be useful? Essentially what's going to happen is that if we discover that erater is a known function, then we go figure out what its body is, and then we turn this into lets. Now what that means is that if this expression ends up being simple, then it's going to get inlined here, and maybe it's going to flow into the body and allow us to go off and perform more constant folding or something like that. Now, the main challenge with this is that you don't want to do this arbitrarily long. What do I mean by arbitrarily long? What I mean is that imagine that we had that even odd function where we know that we're calling even and we're giving it 99. So you could, in principle, inline that 99 times. Because you would just, inline the call to even, which would have a call to odd, you'd inline that, and you could actually reduce that entire computation to a single value. And so, how can you think about doing that? Basically, here's the way that I would think about doing it. You could make it so your optimizer has this thing that's called gas. This is a very common idea in optimization, where essentially what happens is every time you do an inlining, it costs 1 gas. And you can only inline if gas is positive. And this now just puts a cap on how many times you're going to inline. And you can tweak this a little bit, because what you could do is you could say something like, if E0 through En are actually literally constants, not like variables, right, but actual constants, then have that not take gas. And why would you do that? The idea is that if they're actually constants, then that means that you have completely removed whatever residue there was from the fact that there was a previous call, so presumably that's going to stabilize. But now, I mean, this obviously can be defeated by crazy things like, you could write, um, define f that takes in an x, um, which is an S64, and returns an S64, and its definition is f of 0. Okay, so this program right here, uh, if you use this rule that I just talked about, it would inline forever. So anyways, so this gas concept is a way to make sure that every time you inline, you decrement this counter, and eventually the counter hits 0, and then you stop inlining. There are more sophisticated things that you could do, like you could do something like, record the fact that you're inlining this particular function, and you're inlining at this particular argument, and so you could detect when you're going to do the same thing, and then you won't do it again. But of course, you could just defeat that by doing something like changing this to x plus 1. Now, if you had a concrete call like f of 2, then this would inline forever because it would make your optimizer actually evaluate the program, which diverges. So gas is a way of avoiding that problem. It would make it so that the divergence only happens when you run the program. Okay. The next thing that we want to do is you want to update your Uniquify. And as I mentioned before, it can be convenient to actually have Uniquify happen before. You could have Uniquify happen before type checking if you want to modify the global environment. But basically, the only thing that happens differently with Uniquify is that you have to treat each function separately. So Uniquify treats each function separately. And it, when you Uniquifying the arguments is just like Uniquifying, lets. Okay. The next step that you want to do is the step that's called reveal functions. And what the job of reveal functions is that we want to find all references to functions, funds, and replace them with this funref form. Again, I've mentioned this a few times. This is something that you can kind of do inside of the type checker. Basically, there's one version of this program that does this. It uniquifies, and while doing uniquify, it also does reveal funds. And then you take that and then you use that in the type checker. The other perspective is that you could make it so that the type checker runs, and while it's running, it also does reveal funds. And then after that, then you uniquify. Finally, you could, just do these completely separately. You could do type C, and then from there do uniquify, and then from there do reveal. There's no right way to do it. They're all kind of separate ones. What I would recommend doing is this style. That's the style that I think works out the best. Okay, now the next pass that we need to implement has to deal with the following problem. Okay, so on x86, and I of course mean x86 64, functions always have 6 arguments. Those arguments are always RDI, RSI, RDX, RCX, R8, and R9. You can't have a function that takes more than that. Now, of course, you've written a C program before that has more arguments than that. So what am I talking about when I say they don't have more than this? Well, different operating systems and platforms and standard lib implementations provide different rules for how you should deal with passing arguments. And so what I'm describing is the standard x86 ABI. But that standard ABI uses these six arguments uses these six registers for passing the arguments. And then after that, they basically just say, now the operating system decides how you pass more than that. Now, sometimes what you do is you pass them on the stack. And which order do you pass them on the stack? There's all these different things. Essentially, what we need to do is come up with our own way of doing it. So in our R language, you could write a program, you know what I mean, where it has, F, A, B, C, D, E, F, G, and H. And so that's more than 6. So what we're going to do is we're going to make a pass. It's called limit functions. And its job is to find functions like this and turn them into functions like this, where they take F, A, B, C, D, that's the first 4, the 5th argument, and then the rest of the arguments come as a vector. F, G, and H. So what this does is it makes it so the early arguments are passed as registers and later arguments are passed as a vector. Okay, now how do we actually do this? Essentially, all we need to do is 2 things. So thing number 1, modify function definitions. Modify function definitions. And 2, modify function applications. Now, notice that we're going to do this to every single function. So that means that we don't need to know which function we're actually calling when we modify the applications. We just need to know the fact that it is being called with more than 6 things. Okay, so here's how it works. So what's going to happen is that you're going to walk through your definitions, and you're going to see a definition like this. It's going to say define F, and then it's going to have A, which is type A, and B, which is type B, C, which is type C, D, which is type D, F, which is type F, and that's 1, 2, 3, 4, 5, and so the ones after this are the ones that are big. Then we'll have G of type G. Oh, I forgot E. E of E, F of F, and then G of type G. Okay, and then that's going to return some return type, and then there's some body B. Sorry, some body E, body. Okay, so you're going to identify something like that. And what you're going to do is you're going to transform this into the following. It's going to be a new definition. It's going to have the same function name. The first 5 arguments are all the same. So A, B, C, D, and E. Okay, so the first 5 arguments are all the same. But then the last argument is a new name that you're going to come up with. I'm going to write it as rest, and it's going to be a vector of TF, TG, and any other ones, right? And then you're going to return the return type. Okay, but now you're going to have to modify the program. And the way that you modify your program is you add in an additional let, and this let is going to say, let F equal vector ref rest of 0, and let G equals vector ref rest of 1, and then this is all inside of the E body. Close the let, close the define. So what we did is we took all of the functions, we found all the arguments after the 6th one, and we wrapped them in a vector. Now, it's really easy to write this program in a dumb way where you accidentally make it so that if there's exactly 6 arguments, you turn that into a vector. So don't do that. Only have it apply if there's more than 6. Okay, but now that was just step 1, modifying the function definitions. We also have to modify the function applications. And so what we're going to do there, 14.9, is that you see a function call and you're calling some function, and you have argument 0, argument 1, argument 2, argument 3, argument 4, argument 5, 1, 2, 3, 4. Actually, oh, it's annoying. I'm going to get rid of this 0 here so that we don't have like off by 1 in our brains. Then we have argument 6, and then we have argument 7. Okay, so you're going to identify syntax like that, and you're going to turn it into f of argument 1, argument 2, argument 3, argument 4, argument 5, and then boom, wrap these in a vector, argument 6, and argument 7. All right, and so now what you've done is you've made it so that whatever function this ends up being, it now is obeying the correct for. And that's all we need to do. Okay. The next step is to modify our RCO pass. So the only thing that we really need to do with our RCO pass is that we need to change function applications. Because really the only thing that we've added function references, the definitions themselves, and then function applications. So this is the RCO. So basically, step 1, let funrefs be a new simple category. Okay, that's easy. You sort of get that for free. Okay, step number 2 is that we used to have programs that looked like this. They just had program and then some info and then some E. But now, this is old, but now what we do is we have a program and it has some info and then it has some sequence of definitions and then it has an expression. Well, what we're going to have to do is we're going to have to change that into a program. Yeah, and we, by the way, change this into a program with some info, and then we modify that expression to E prime. Well, here what we're going to do is we're going to have that info, and we're going to modify the definition, each definition. So we're going to go through each definition and do the RCO pass on it. Now, what I recommend doing is actually do one more thing, which is that take this E right here and turn it into a function. So add another definition that defines the main function, that takes the arguments and returns whatever E's type is, and it just has E as its body. And then say that this thing, had better be like 42 or something like that. Or if you want, you can have it be a call to main. The idea is that we're now going to make it so that one of the jobs of RCO is to uniformize the program so that everything is a function call. Sorry, everything is a function body. But now the third step is deal with applications. And that's what we'll talk about next. Okay, so this is 14:11. Okay, so we're gonna intercept a call to RCOA with some renaming environment, and it'll tell us whether we're in tail position, and then we'll have an application to some operator, and then some operands. Rand 0, ... rand n. Okay, so what do we need to do? Basically what we need to do is we need to go off and call RCOA on every single one of the operands. So we'll say let rand result equal mapping calling RCOA sigma, and it's not in tail position, so we'll pass in a false on all of those operands. So we'll go off and call ourselves recursively. Now remember, that means that we're going to get for each one of those things, we're going to get the new variables it needs and then the argument for it. Then what we're going to do is we're going to get the new variables for the operator, and we're going to get the argument for the operator when we call RCO A with sigma and false on the operator. Then what we're going to do is we're going to get the new variables for the operands, which is basically going to be appending everything that happens when we get the first part of the rand result. So that's going to go off and grab all of the different new variables. We're going to append them all together. And then we also need the arguments for the rands, which is going to be just mapping second over the rand result. So we're going to go through all those results and just grab off all the operands. Okay, so now what do we need to do? Basically, what we're going to do is we're going to treat calls that are in tail position special. This is going to make it so that we don't accrue stack space when a call occurs in tail position. So what we'll do is we'll have a test that says, are we in tail position? If we are in tail position, then we can just return the new variables. Oh yeah, sorry. And let me just move this, or erase, and then I'll rewrite it. And then the new variables are just the new variables for the operator combined with the new variables for the operands. Okay, so if we're in tail position, then what we'll do is we'll return the new variables, and then we need to return an application to the argument for the operator and the arguments for the rands. Otherwise, what we'll do is we're not in tail position, so in that case we need to generate a new variable. So we'll have all the new variables plus one more, which will be saying that the answer is an application of the new argument, and we'll return that final answer. All right. So this is the new case that we need for application, and we don't need to change RCOC because RCOC calls into this. So we're not going to be able to look through function calls and figure out what comparison they do. It'll just turn into an application form. All right, so that's all we need to do for the R language. What we'll do next time is we'll talk about how to modify the C and X languages to deal with function calls. So, see you next time.